similarity, and that's what we're going to kind of focus on. But in order to get to that point, we have to have a foundation of ratios and proportions. Everybody needs to be on the same page in regards to what those are, what they mean to us, and how we can use them and apply them. So I guess the first thing to do is talk about what a ratio is. Okay? I got two definitions up there. I don't like the first one. It's kind of too wordy. It says the ratio of one number to another is the quotient when the first number is divided by the second. I think you can, we always talk about how definitions should be concise. I think that one's not very concise. It's very wordy. If you look at the second one, that's the one that I would write down if I were to do the comparison of two numbers through division. The comparison of two numbers through division. That's a ratio. Okay. And if you know anything about our groups of numbers, okay, obviously we have our real number line, right? Okay, which is every number that we can possibly think about, at least at this stage in our math careers. When I think about rational numbers, what is the root word in rational? Ratio. Okay. So your rational numbers we've talked about as being, we've defined them as A over B, where A and B are, write it that way, we read that as elements of integers. Okay, integers are just your 0, 1, 2, 3, 4, those types of numbers, and they're negatives. And if I compare any of those groupings, any two of those numbers, I get what we call our rational numbers, which will allow us to create numbers like 0, 1, 2, 3, 4, 5, 6, 7, and their opposites. Put them all over 1, right? Or we'll get things like 1/2 and 2/3 and 4/5 and 12/13 and 11/74 and stuff like that. Does that make sense? Okay. So that's where the word rational comes from. It deals with ratios. Okay. There's going to be a huge portion of Algebra 2 that deals with rational equations. So it's equations that incorporate fractions, and that is compounded even further in college algebra and trigonometry. We deal with rational equations and expressions all the time in those two courses. So this is not only good for the geometry that we're going to learn, but an understanding of what a ratio is going to be really easy, or make things a lot easier for you in those other courses as well. Your denominator cannot be 0. Okay, so when we divide, obviously we know division by 0 is impossible. It's an indeterminate value. We don't have a number that is defined for that division of 0. Okay, so one other idea is there, that last phrase is just a reminder for you. When you're typing your answers in, make sure they're in simplest form. Okay, if I get 3/6 back, I better put that as 1/2, or Math Excel is going to count it wrong. And of course, exam is going to want the 1/2 instead of 2/4 or 3/6 or whatever. And you'll probably lose points if you don't reduce things. So make sure that you do that. There will be times where the unreduced version of the ratio is beneficial to us. The 3/9 that I have in that example above, that might be beneficial to setting up an equation. But the 1/3 is going to be beneficial in regards to solving the equation. Does that make sense? Okay. At any time, if I can reduce before I do any algebraic calculations, it's probably beneficial to do that reduction. Okay. An additional way that you might see these written is that way. Okay. 3 and then a :9. They all read the same way, 3 to 9. Okay. Whether I write as a fraction, I use the word 2, or I use the colon, still read them all 3 to 9. Okay. Or if I reduce them, they're all read 1 to 3. Is that okay? Okay. And hopefully you've maybe seen that before with the colon of how we compare numbers. If you've ever done odds in probability, you use that notation to talk about the odds of something occurring. Just some examples here. It says find the ratio of AC to BD. Now it's important how you read this. It says AC to BD. That means if I'm going to write it as a that notation, okay, and AC needs to come first. And if I'm writing it as fraction notation, then AC needs to be your numerator. Does that make sense? The first thing you read is your numerator, second thing you come across is your denominator. Because I want you to understand that AC to BD, AC over BD, is completely different than BD over AC, right? Okay? When I go ahead and evaluate this or plug things in, AC, what is AC in this question?
6R.
6R. Okay? So you get 6R up top. What is BD? 20. Okay? So what I want you to understand is that 6R over 20 is completely different than 20 over 6R, right? They are reciprocals of one another, but they're completely different, all right? Because of how we're going to use them later on. Now we should reduce this, and they both reduce by 2, right? Take a 2 out of the top, take a 2 out of the bottom with division, and I get 3R over 10. Okay, and that's that ratio. But my argument is that is different than 10 over 3. If I just said 3 over 10, let's just look at 3 over 10. Let's say I'm going to use this ratio and apply it to another distance and see what that other distance has to be. So let's say that I take 3 over 10 and I'm going to multiply some segment length of, let's say, 100 by that 3 over 10 and see what that takes that 100 down to. Okay, so if I take 100 and multiply it by 3/10, it's going to shrink that 100. Does that make sense? If I take 100 and multiply it by 10/3, what's that do to that 100? Makes it bigger. Okay? So it's always important to understand whether I should be using 3/10 or 10/3. It's reciprocal. Okay? And it's all about the order that you compare. This one says AC to BD. It tells you your numerator and your denominator. The second one here, find the ratio of angle C to angle D. Angle C is what here? 80. Angle D is 40, right? They're both, I didn't put my degree symbols up here, but they're in degrees. So what's that going to reduce to? 2, right? And if you want to write it that way, that's fine. I think it's beneficial and thoughtful to put that denominator of 1 in there as well, because eventually, and obviously, it tells me that angle C is 2 times as big as angle D, right? Okay. So I want to see that 2 to 1 relationship. Okay. Okay, there. Okay. Find the ratio of angle B to angle D. It says same type of question, but do I know angle B up there?
No.
No. So we need to rely on some of our prerequisite information. How many degrees should all 4 of those angles add up to? 360. And right now I've got, what, 190 and then 230, right? So how many degrees are left over for B? 130. So now compare B, 130 degrees, to D, which is 40 degrees, and that should give me 13 over 4. Okay? Now I'm using, I kind of maybe neglected this or overlooked it. I didn't put units on the segments here. Let's talk about the units of the angles. Okay, this should be 80 degrees and 40 degrees, right? But when I reduce, I change that to 2 over 1. The degrees reduce as well. They cancel each other out. Degree divided by degree is the units are going to cancel. Does that make sense? And they actually divide to a factor of 1. So when we compare things, we like our objects to have the same units. Okay? For instance, if I would have had if I'm looking at this one here, and I'm getting this result back of 2, what does that 2 tell me? Okay, it means that one of my angles is twice as big as the other, right? In total disregard to the units that we use to measure the angle. Okay, so if my units that measure that angle were in degrees, I know that one of them is twice as big as the other one in degrees. If the measurement we use is radians, which is another type of measurement tool that we use for units that we use for angles, then I would know that angle C is 2 times in regards to its radians measurement than angle D. Okay, so it doesn't matter. That 2 is telling me how many times bigger something is, how many times smaller something is, and the units should cancel. They shouldn't matter to me. Okay. Same idea here when I'm talking about distances. If the 6R was in inches, my whole sum at the 20 would be in inches, right? Okay. I want to compare inches to inches, or feet to feet, or miles to miles. I never want to compare inches to miles. Does that make sense? If I ever go through work and I get a fraction that the numerator is in inches and the bottom is, or the denominator is in miles, I need to change one of them so they're both in inches or they're both in miles. Does that make sense? Okay. So that's what that last thing there says. Compare objects with ratios. The measurements need to be in the same units. Okay. We want inches, miles, we understand. Now that being said, that's not something we can always do. Okay. Something you guys are. Some of you may have driven to school today, right?
No.
How fast you drive to school today?
Oh, about 40.
40 what?
Remember when you went like 90?
Okay, you went 40 miles per hour. Okay? So you went 40 miles for every 1 hour, right? So that's a ratio. Okay? However, the unit of miles cannot change to a unit of hours, right? There's no way we can take a distance and change it into time. There's no way we can take time and change it into distance, right?
Yeah.
Like we can take inches, which is a distance, and miles, which is a distance, and change one or the other, right? Because it's converting a distance to a distance. But you can't take a distance and change it to a time. You can't take a volume and change it into a length. Okay, miles per gallon, right? You all heard that? MPG?
No.
Okay.
Oh, yeah.
You see car commercials all the time, right? They say this car gets 40 miles per gallon. Okay, well that's a rate of how many miles you get for every gallon of gas that you use. You can't change miles into volume. You can't change the distance into volume. So we leave it as miles per gallon. Okay, so in the event that you have units that cannot cancel, you end up with what we call a rate. Okay, speed, sometimes referred to as rate.
So like hotels.
Okay.
Like,
Like per night?
Oh, per hour.
Per hour?
Yeah, like. Oh, like the crack hotel we stayed in.
Yeah, I mean,
Per hour.
some of you have jobs, you get hourly rates, right?
Per line.
You make $13 per hour. Okay. Money cannot be converted into hours. Okay, and hours cannot be converted into money. So it stays as a rate. Okay. Hopefully, you guys know that you are on video. Things you say are things that are going to be all the time, right? I can go back to it and listen to it again. And if I need to turn into Jesco, it's there. Okay. Quit saying stupid stuff. All right. So bonsai trees. Okay. Just to get you an understanding of what this is. You guys know what a bonsai tree is?
Yeah, it's like a tree that's like that tall.
Okay, so in the Japanese culture, you see a lot of these. If you go to like the Tokyo Steakhouse or something like that, they might have some of these in the lobby or whatever. They're just miniature trees. A lot of people use them as like hobbies, and they manicure them for your feng shui. Yeah. They're just like indoor miniature plants. Okay, trees.
They really are.
They shape and stuff like that.
Like that.
This question is referring a bonsai tree, a very small tree, to a full-size outdoor large tree. Okay? And they're saying that the bonsai tree is 15 inches. The outdoor tree, that they call it a senator, is 118 feet. Okay? So obviously quite a large discrepancy in their sizes. They want you to come up with the ratio of the height of the bonsai to the senator. Bonsai, 15 inches. Senator, 118 feet. And if I write that down, and this is what I want you guys to understand, this is why we talked about getting the units to be the same. If you take the ACT, or if you take the end of course exam, and there's a multiple choice question on it, that might be one of your options. And a lot of people instantly write that down. Comparing 15 to 118, that's one of my options, that's going to be the answer. Why is that wrong? Okay. Why is that wrong?
But this is not saying units.
It's not saying units. Okay, so we got to change it.
Is this the thing where we like put it like, and then we put another fraction right?
Oh yeah.
And then we like multiply them across.
Yep. So those of you that are in
I
chemistry
love that.
probably have a little bit of an understanding of how to do this. Okay. And we're going to do a lot of this in this class, so hopefully you end up picking up how to do this. It's really not that hard though. Okay. Let's say now I want to get them in both the same units, right? Doesn't matter which one to which. Okay. So let's deal with the easier one. I think taking 118 feet and converting that to inches is easier. What would I do with that 118 feet to get it into inches?
Times it by 12.
Okay. Because you know for every 1 foot you get 12 inches, right?
Yes.
The reason we do it that way, and this hopefully this makes sense to you for what we're going to do later, because going from feet to inches, that's a direct link from Like, I mean, they're really close units to one another, right?
Yeah.
Okay. If I want to go from like feet to kilometers, okay, one, they're not really that close, right? Okay, and two, they're in different systems. So there's a lot more multiplication that needs to occur. This one shouldn't be too bad. Probably take feet, 2 inches. But regardless of what you start with and what you want to end up with, you would do the exact same approach here. It just might involve more multiplication. So this is the way I think you should probably set this up. You always start off with a fraction. Okay, put it over 1. It's going to help you realize what you need to multiply by, or you're always going to multiply by fractions. Now, I'm in feet, and I want to get to inches, so I always write my units over here. Okay, if you're in a class, and I did this with my trig students, it was probably 2-3 weeks ago. We did a problem, and we got an answer of like 60 miles per hour. Okay, somebody else in the class got the answer to be 60 feet per second. We both got 60, right? Same quantity, same numerical value, but the units were different, right? So one of us was right and one of us was wrong. Because something traveling at 60 miles per hour is traveling at a completely different speed than something traveling at 60 feet per second, right? Does that make sense? So the units are as important, if not more important, than the numbers that you get with those units. Okay? So what you want to do is you start with the unit that you're trying to convert, and you write over here the unit that you want to convert into. Now the idea is, if I were to start multiplying through right now, in the numerator I have feet, in the denominator I have nothing. Okay? Well, I want to be able to multiply through so these feet disappear. And through division, the only way I get things to disappear is if they divide out to give me 1. Does that make sense?
Yep.
Okay? So I've got feet up top. Where am I going to need feet to show up?
On the bottom.
On the bottom. Okay? So now, is there, and I always ask myself this question, when I write down a unit in that next ratio, I'm always going to ask the question, is there a direct link from that unit that I just wrote down into the unit that I want to get my answer in? Is there a direct link from feet, that feet that I just wrote down, to that unit of inches? Yes. So that's why I put inches right there, because there's a link between feet and inches. Now think about what would happen if I were to multiply. No, don't even worry about numbers right now. If I multiply this out, you'd have feet, inches up top in units, right? And on the bottom, you would just have feet. So you have feet times inches up top, and I have feet on the bottom. What's that going to do? Cancel out. They are a factor of 1, essentially. Feet divided by feet gives me 1, right? Something divided by itself always gives you 1. So you're left with just inches, correct? So that's the process that we want to go through, is work through here to see if we can get our units to cancel out, being left in with the only unit that needs to be left in our answer. Okay? And eventually there might be 2 units that we want left in our answer if we're talking about rates. Okay? Once we have these units set up, now we go in and fill in the numbers. Okay? Don't we know 12 inches for every 1 foot?
Yeah.
Okay. So now that I have that, can I go straight through and multiply?
Yeah.
And that will change this number into 1416. Okay? So 118 feet is the exact same thing as 1,416 inches. The inches on top and bottom will cancel there. And it's going to be 15 over 1416. I believe the 1416 is divisible by 3, and so is the 15. I want to say it gives me 472. Okay. So I think I can, let me just double check real quick. $14.16 divided by 3. 472. So this thing does reduce to 472. Oh, one second on the bottom. 472 on the bottom. Divide that by 3. Divide that by 3. And 5 on top. So that is the ratio there. Okay, that's the comparison of the bonsai tree to the bold cypress tree. Okay, the senator. Okay. Now, why is that useful? We now have essentially kind of a comparison that so let's say that comparison is true for any 2 cypress trees one being a bonsai and one being the actual tree outside. And say, okay, somebody tells me that I have a bonsai tree that is 10 inches tall. I could use that ratio to convert that 10 inches into how big the actual tree outside would be. Does that make sense? Okay.
How do they get them to stay so small?
Say what? Small.
Bonsai trees. The bonsai trees.
They just give them a little bit of water.
Really?
I don't know.
I think that really is what made them in their DNA. When their DNA was cross-multiplied with the other DNA in the two original base trees, I think it had.
Right. It's probably it's genetic.
I really just hurt my feelings.
So we had 15 inches over 118 feet, right? And we changed everything in inches, but it shouldn't matter. Okay. The person that changes everything into feet should come across the same conclusion. So let's try that. Let's say I got 15 inches. I want to change that into feet. Okay? So feet should be my answer. I've got inches up top right now, right? So I need inches down here. There's a direct link to feet. So what number should go here? 12, right?
Yeah.
12 inches for every 1 foot, correct?
Yeah.
Now if I multiply those through, I get 15 over 12, correct?
Yeah.
So 15 inches is the same thing as 15 twelfths feet, right? And you put that as a decimal if you want to, but I'm not going to because of this reason. I have 15 over 12, and that's feet now, right? So that ratio right there means the exact same thing as that 15 inches. I got 118 feet on the bottom. What's going to happen with my feet? Feet over feet, those units are going to
Cancel out.
cancel. All right, so now you got a fraction divided by fraction. We know how to divide a fraction by fraction?
Yes.
How?
You do the top fraction first.
Multiply what?
The reciprocal of 1.
Okay, so we'll take the bottom one. We take this 118, find its reciprocal, and multiply by the top, right?
Yes.
So it gives me 15 twelfths times 1 over 118. What's 15 times 1? 15. 15. What's 12 times 118? 14, 16. Is that the exact same 14, 16 that we got earlier? By changing everything into feet, or sorry, inches, right?
Yeah.
Okay, so hopefully that exercise shows you whether you're a person that wants to go to feet, change everything to feet, which I think would probably be a little bit harder in this case. You still get the same answer that anybody that would change everything into inches would have got. Does that make sense? So when sitting there thinking, does it matter? No, it doesn't matter. But in regards to maybe the amount of work or effort or knowledge required to do it, it does make sense to change everything, in this case, I think, to inches. If in converting things, the easier thing to do is to take the larger units and convert them to smaller units. Because when you do that, you're multiplying. Okay? And people would probably prefer to multiply than divide, right? Would you rather multiply 118 by 12 or divide 15 by 12? You'd rather multiply, right? It's a nicer number. It's a whole number. Division would give me a fraction. We get to things called extended ratios, and this is just being able to compare, instead of just 2 numbers, we'll compare 3 numbers or 4 numbers or 5 numbers together. Okay? So here I'm just showing you comparing 3 numbers, A, B, and C. That's how we would write it. But what that means to us is that each one of these comparisons would be true. A compared to B, or A over B, B over C,
Or A or C.
or A over C. All of those would be true if I say A compared to B compared to C. Does that make sense?
Mm-hmm.
Now you can, like I said, you can have multiple things there. You could have a D, an E, and an F. Okay, you can have 6, 7, 8 things if you want to. If we can understand it with 3, you should be able to do it with as many as they ask. So here's a question where extended ratios are existing. It says you have a triangle in which you know the perimeter is 190 units. They say that the side lengths, they've taken the side lengths and they've compared them in a extended ratio, and they reduced to 4, 6, and 9. They want you to kind of work your way backwards. If the 3 side lengths reduced to 4, 6, 9, can you work your way backwards to figure out what the actual lengths were? So here's the idea. This is 4, and that's 6, and that's 9. Thinking about perimeter, what do those add up to? 19. Is that the 190 that I needed?
Yeah.
No. So maybe the question is, okay, so obviously they weren't those aren't the initial values of that triangle. Maybe they were 8, 12, and 18. Do you see if I compare those, they still reduce to 4, 6, 9?
Yeah.
because there's a factor of 2 in all of them, right? Do those red ones add up to 190?
Yes.
No. Okay. What about taking this 4 and tripling? So that would be 12. Take this and triple, it gives me 18. Take this and triple, it gives me 27. If I add all of those up, do I get 190?
C.
No. Okay. So that value of 2 or 3 or 4, I'm not getting to that 190 very soon or very quickly. Okay. But hopefully you guys realize that we're trying to enlarge this number, this 4, to something. We're trying to increase that 9 to something and trying to increase that 6 to something, right? But they all need to increase by the same amount. And when we're talking about this with ratios, increasing is a multiplication idea. So I need to increase them all by some x. Does that make sense?
Yeah.
Multiply them all by 2, or multiply them all by 3, or multiply them all by 4. And I don't know exactly what that number needs to be. So this should give me that 10 that you're talking about. If I'm talking about perimeter, 4x, 6x, 9x, just look at that just that way. We all have an x in it. Yep. So it reduces to 4, 6, 9, right? Hold. If I add them together, I should get 190, so looking x to be 10. Okay? And then we get 40 to 60 and to 90, and those are the 3 values. The math Excel assignment is it's going to be open, but it's not due tomorrow. You can start it, but it's not due tomorrow. Great.